for engineers.
Oh my god, I wish I was though.
Who are you looking for?
Jerome.
Yes, he is in the
Upstairs.
building, but maybe upstairs. Because I saw him. Okie dokie. No problem. Not yet. Okay. Next lesson. Another bank meeting today. But maybe this is the last one.
Why are they talking so much time?
Because you meeting to do this, meeting to get the mortgage, meeting to get the insurance, meeting to get another insurance. All the meetings.
How long the meeting?
1 hour. Because then they have to say, do you want this insurance and this one?
I think they should do it in email.
I try to do as much as I can in emails, but some things they want you there. Let's see. Okay, next lesson. You will need your calculator.
I have two calculators.
You'll need a good calculator. Okay. My other students aren't here yet. We'll start, but we'll go slow. We have class later today, but remember I said I want to bring it earlier, 1 hour earlier, so we can finish sooner. No. Correct. Yes. Actually, we can finish. If we start. You see, I'm in this room. If we could start at like not 10 to 1.
We can, because we finish this class at 11, so we can.
Yeah, and then you're off for 2 hours.
Mm-hmm.
So not 1 o'clock, but 10 to 1. 12:50.
We're doing from 1 to 3.
12:50. Here we are. You were supposed to have class at 2 to 4, wasn't it? And I'm saying we move it from 1 to 3. But not actually 1, 10 minutes sooner.
Right.
So we can finish at half. So we can finish at 1:30. You get what I'm saying? So we'll do, I'll type it here. 12:50 to this time in B302, this room. I told you this last week and I said I would remind you this morning. Congratulations on making it to school. Did you walk?
No.
Drive?
I got the car yesterday, so I had to come today.
No speakers. We're actually doing a new lesson. Right. Ready, Musharif?
Yes.
Yeah. Okay. This is today's lesson. Einstein's equation. At least I think it is. Yeah, lecture 6. As you can see, a big enough lesson, but a very important lesson in the study of atoms. You got this? Einstein's equation. Yeah? Okay. Here? Yeah. Continue?
Yes.
Okay. Now, because obviously a proton and a neutron are so small, we don't use kilograms, because I mean, we could use kilograms, but kilograms too big of a unit. So we have a different unit which we'd like to use for measuring mass, called the atomic mass unit, or AMU for short. The symbol is U or AMU. I usually use the letter U. So this is the value of U. Now, wait, before you write it down, let me explain the idea behind it. 1 AMU is roughly the mass of a proton or a neutron. So it means, for example, if I have hydrogen, which is 1 proton and 1 electron.
1 neutron and 1.
No, 1 proton and 1 electron is hydrogen. Yeah. And hydrogen 2 would be 1 proton and 1 neutron. And hydrogen 3 would be 1 proton and 2 neutrons. These masses would be roughly 1U, 2U and 3U. So in other words, it's a convenient unit for atoms. Now I said it's roughly the mass of a proton or a neutron. So later we'll see it's not exactly this, it's nearly this. Okay. In fact, you might recognize the number 1.66 times 10 to the minus 27. That was the mass we had earlier for protons or neutrons. And, Mary, if you open the lid on your calculator, and your calculator too as well, if you look at the lid, yeah, one of the constants is for AMU, or it might be called U. I don't know which one it is. Yeah, could you find it as well? We'll get it up here. You're looking for something that says AMU or U? Did you find it? Well. Don't show me your phone, dude. I don't care what your phone says. Dude.
No.
You're not even sitting down yet. Come on, you're not even sitting. You're literally not even sitting down yet.
Doesn't make any difference.
Does to me.
No, it doesn't.
I am marking you absent for the first class. If you have a problem, you can talk to Connell about that and explain it. All right. 17 it is.
It's AMU.
Yeah, 17.
So,
Come in. One sec.
yeah. A lot of.
Oh my goodness. Of course, Ian, I'm marking you absent for the first class.
Yes.
Yes, okay. Hey, right, so you can see on the calculator, what would we say the number it was? I forget now.
17.
17.
Yeah.
Yeah, okay. Now you can write it down. Continue? Oh, you're teaching them how to get the
Yeah.
constant up.
What?
Okay.
Got it? Okay. Note the mass of one proton or neutron is about 1 AMU. Okay, continue. Right. Consider the following. You have one hydrogen and you fire on to one lithium 7, hydrogen 1, and it forms 2 helium. Is this equation balanced? Well, let's have a look. How many protons do we have here?
4.
4. And here?
2.
No, 4, because of the 2 here.
Yes.
And how many nucleons? 8. And here? 8. So it looks balanced, right? It seems to be. Now, have a know what the mass is here. The mass of hydrogen is about 1.007 AMU. The lithium is about this much, about 7 AMU. And helium is this much. As a small exercise now, I just want you to calculate the mass on the left of the equation and the mass on the right of the equation and tell me what you get.
Yeah, it's almost the same.
But not the same.
Yeah.
Which side is bigger?
This side.
Which is called the left or the
The
right?
left side.
The left. Did you get it there? What did you get?
Is it close?
Oh, that's a personal opinion. What did you get on the left?
1.67 multiplied to minus 27.
Well, no. You can leave it in terms of AMU.
It's 8.02.
Yeah, so you could say 8.023 AMU.
Okay.
Yeah?
Oh,
Okay, and then on the right, what do you have?
8.004.
8.004. So 8.023 is more than 8.004. So what's going on? The mass has changed. You see, the mass is not the same. But mass doesn't just disappear, it has to become something. Oh wait, or does it? Dun, 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 dun. So in other words, the equation is not balanced. We're missing something at the end here. There's something extra. Walton didn't just do this experiment one day. This is Cockcroft and Walton experiment where they fired protons at lithium to make helium. And the reason they were doing this is they were testing an experiment that they were testing a formula that Einstein had. And Einstein said in his theory that when atoms combine in a nuclear reaction, with some of the mass appearing to be lost, it was not lost, but rather changed into energy. And in fact, not only did he say this, he provided the world famous E equals mc squared formula, where E is the energy created and m is the mass lost. So what happened in the Watford experiment, the mass didn't disappear, the mass was converted into energy. Yes. Let's see if we got an example now, or... Yeah, so here is the Watford experiment again. Hydrogen is fired at the lithium to make helium plus some energy, and here again are the masses. So the first thing I want you to do is find how much mass went missing in the reaction. So just minus the 2.
0.019.
Okay, write that down. 0.019. Yeah. Okay. If we want to use and of course we need the unit. What's the unit here for this mass? AMU. Of course, if we want to use Einstein's formula, we need to change this into kilograms. So using your calculator, can you change that into kilograms? 0.019, was that it? And the constant number 17? Yeah. What's wrong, Mushari? I think this meeting didn't go well. Right, we convert this into kilograms. Yes? And this is how many kilograms I get. Now, using Einstein's formula, we can change this into energy, which is, sorry, I might have actually flicked through that too quick. Did you write down the formula for Einstein? Yeah. Well, you don't really need to write it down because I think everybody knows this. Although maybe you've never actually used it before. Got that? Yes? Okay. Continue? Right, so we'll go back to the calculator. This is the mass. You might need to write that down in kilograms.
My mass is different to a different one.
Huh?
Like the values are different at the end.
You have 0.019U?
Yeah. It's 3.155, 023, 686.
What calculator are you using?
Same. This is common remember last week.
Don't know. Okay, now let's use Einstein's formula, which says the energy is M, which I have in my calculator, times C. Now actually C is on the calculator as well. I think it's C0 perhaps on the calculator. 28. Yeah, squared. Yeah. This is the answer in joules. -6 is micro, 9 is nano, 12 is, pico? Anyways, 2.84 times 10 to the minus 12 joules is the answer here. Okay, that is the energy created from the reaction then. Okay, did you write that down? Yeah? Got that? Yeah. Okay. Next now. Yeah, there's nothing really else to say. The only thing that could be different in the exam is they might ask you to convert this into electron volts. So does anyone remember what you need to do to get this into electron volts? Divided by that E constant. What number is the E constant on the calculator? Oh yeah, 23. So that's a lot of electron volts. So I know the answer in joules seems small, but when you convert into electron volts, which would be the right scale because you're dealing with atoms, then you realize the energy is quite big compared to the mass. It's actually a lot of energy. Because you can't really measure in joules because joules are too big. When you use electron volts, you see that, you actually have a lot of energy compared to the mass. Do you get what I'm saying about using the right unit? This is actually quite big for what's happening because this is only one atom. Alright, next now. This is the mass of hydrogen, which is 1 proton, no neutrons here. The mass of a neutron is this much. This is the mass of a proton. This is the mass of a neutron. So can you use the calculator and tell me how much hydrogen 2 would be? What's in hydrogen 2?
One proton and one neutron.
Correct, 1 proton, 1 neutron. So can you tell me what the mass of hydrogen 2 should be? There's the mass of a proton, there's the mass of a neutron. Tell me what it should be if you add them.
Why is this hydrogen two, not hydrogen one?
This is hydrogen 1 proton. I want to know what's the mass of hydrogen 2. And add in a neutron, yeah. So the mass should be, did you get this number?
Yeah.
Should be this, right? Now, let's continue the idea and do it for 2 protons and 2 neutrons, okay? So can I just backspace here, put a 2 here, and, oh my goodness, a 2 here. Do you remember what 2 protons and 2 neutrons are called?
Did you?
You weren't here.
Oh, sorry.
2 protons and 2 neutrons, do you remember what that is? The alpha particle. Remember? This is 2 protons and 2 neutrons. It's an alpha particle. Anyways, the mass should be 4.03. Is that what I got here? Yeah, 4.031882. 4.031882. It should be that if you add 2 protons and 2 neutrons. But in fact, if you measure the mass of an alpha particle, it's this, 4.002602. It's less than what you think it should be. So if you think about it, what you're saying is, you have 2 protons, 2 neutrons. You stick them together to make an alpha particle, and the mass is less than what it was before they were stuck together. Which, if you really think about it, is very strange. Like, why should it get less just because it's stuck together? It should be the same, right? Right? It shouldn't be different. So 0.02928 AMU is missing. This missing mass is called the mass defect. Now, it's not actually missing. So what's happening here is that missing mass wasn't missing. It was converted into energy. And you might say, well, what energy was it converted into? It was converted into energy to stick them together. Because if you think about it, if you have a proton and you have a proton, they're both positively charged. Should they stick together? No. So the energy required to stick them together is coming from the mass. Do you get what I'm saying? It's like the sticking energy is drawn from the mass. So this is called the binding energy, and it's the energy required to hold the nucleus together. And this energy, the formula to calculate it, guess what, is mc squared as well, where m here is the missing mass, which we call the mass defect. That is the loss of the mass. Okay, if you can make note of this definition of binding energy. Got that?
Nine.
Oh, you have it already?
Yes.
Yeah. Now, the last point here is that this energy is also the energy you need to separate the nucleus. So what I mean by that is, if you have a proton and a proton stuck together, and you want to know how much energy you need to separate them, it's equal to this binding energy. Yeah?
Yeah.
Okay. I think it's also worth adding that last line in too. English, please. Okay, you wrote this down? Continue. Okay. So, in an earlier lecture, we saw that the weak nuclear force is trying to push apart the nucleus. Do you remember what the weak nuclear force causes? What is it responsible for? The weak nuclear force. No? Sharif? No? Okay. The weak nuclear force is the force that pushes the atom apart, which is what causes the radiation, the release of the alpha and the beta. Usually this is not strong enough to break the atom, because most atoms don't break, but some do, like uranium. Yes? Do you remember this? And do you remember I said there were three things about the weak nuclear force? It's weak, it's in the nucleus, and it's the force, it's a repulsive force. It tries to explode the nucleus, it tries to push things out. So I said at the time there must be some other force that's pulling it back in to balance it, and that's what we're looking at today, called the strong nuclear force. So Newton's law tells us that the atom is not decaying, then the net force should be zero. Therefore, there should be a counterbalancing force. This is called the strong nuclear force. It's a strong attractive force instead of repulsive, which acts only in the nucleus and over a very short range, 10 to the minus 15 meters. It is the force responsible for binding the proton with the neutron, or I suppose the proton with the proton. In other words, it's the force that keeps the atoms stuck together, the strong nuclear force. A force that we've never actually talked about, although we should, if you think about it, we should have been wondering how atoms can stick together, because if you have protons and protons, they shouldn't stick together. Obviously an electron can stick to a proton because opposite charge, but not so obvious as how a proton can stick to a proton. Got that? Continue? Yeah. No, not yet. Got that? Yeah? Okay, continue? Yes? Right. Right, let's do an example calculation here. What is the binding energy of the alpha particle? So, what is in this alpha particle here? What is it made up of? 2 protons and 2 neutrons. Here's the mass of a proton. Here's the mass of a neutron. Let's calculate what the mass should be. It should be 2 times 1.007 plus 2 times 1.008665.
Why?
Mir, why should it be this?
There's 2 protons
Mhm.
and 2 neutrons.
Mhm.
So we took the protons from the hydrogen.
Well, hydrogen is a proton, it's the same thing. 1 proton is 1 hydrogen, it's the same thing. Yeah. This is what the mass should be. It should be this. But what is the mass though?
4.0.
4.002, yeah. There it is there, can you see that? Alright, so first, just write this down. This is what you might say the mass should be this. Should be this. So, the mass should be 4.03133 U. But it's not this. It's 4.002. So if I minus 4.002, do you remember what we called this one?
Mass defect.
Mass defect, 0.02933. 0.02933. That's called, as you said, Mir, the mass defect. So then the binding energy will just be Einstein's mc squared, but we should convert this into kilograms. So let me see, that's times U. No. There we go, that's the mass. Times, and whatever C is, 3.3 times 10 to the 8 roughly. So that is 4.38 times 10 to the minus 12 joules. Now, I didn't say it here, but it's very, very common to use electron volts because the unit is so small. So if I divide this by E to change it into electron volts, no. Yeah, I missed that whole part. 23. That's pretty big. 1, 2, 3, 4, 5, 6, 10 to the 6. 27, yeah. 27.4. Yes, correct. Mega electron volts. MEVs. Yes. I know electron volt is small, but believe me when I say that's really big for the size you're dealing with. Did you write that down? Continue? Yes?
It's always like this.
Yeah, like this. The only difference in the next part is what is the binding energy per nucleon? Same question, second part. So, how many things are in this atom?
Proton and
Yeah, 2 protons and 2 neutrons. So you could work out the total binding energy, but let me give you 2 situations. Let's say here there's 2 particles, and let's say the energy, I know it's not this, but we'll just say it's 1 electron volt to bind them. And then let's say you have, I don't know, 3 particles like this, 3 atoms, and let's say here we say 2 electron volts. Now you might say, oh, this has more binding energy than this, and yeah, it does, but what's the reason it has more? It's because there's more atoms. So it might be more meaningful to look at the binding energy per nucleon. So like here, this would be 1 divided by 2, and this would be 2 divided by 3. It might be more meaningful. So what we'll do here is, if we just put a little bar on the top to say average, and just divide this by 4. That's 6.84 mega electron volts per nucleon. Yeah. Continue. Sorry. Yeah, you have this? Yeah. So this is an important graph for the exam because they sometimes ask you to draw this. So what I've done here, well, not what I've done, but what you have here is, on the bottom you have the mass number, which is the number of nucleons, number of protons and neutrons. So the very first one, what has 1 nucleon number? What's the very first one? It'd be just 1 proton, which would be hydrogen. And then after that would be H2, or it could be helium, which is 2 protons, or it could be hydrogen 2, which is 1 proton, 1 neutron. If you look at the binding energy as you increase the mass number, but if you look at the binding energy per nucleon, not in total, per nucleon, you notice that it's not constant, meaning as you increase, you require more energy per nucleon to hold everything together. But then, once you pass iron, it decreases a little bit. So what does that mean? That means iron is the most difficult atom to break apart. Yeah. It has the most binding energy per nucleon, meaning you require the most energy to break it. So in some way it's like the most stable, because it's the most difficult to fall apart. Do you understand? Now if you look here, the weakest, so to speak, is the first one, which would be something like hydrogen 2 maybe, 1 proton and 1 neutron. It very quickly increases, very quickly. Because this is so low compared to the rest of the table, this is what we use in nuclear power plants, but we'll talk about that in a different lesson. For the exam, they sometimes ask you to draw this. You do not need to remember all the numbers and names on it. What they would want in the exam is firstly to have the X and the Y correct. So on the X-axis here we have atomic number, and then on the Y-axis, you can write this down in just one sec. On the Y-axis we have binding energy per nucleon, and the unit is mega electron volts. And then the maximum happens, I can't remember exactly what iron is, but it's a little bit after 50. So it, roughly increases to a maximum here and then sort of decreases like this. This is what they would want in the exam when they say a sketch, and of course for you to point out that the maximum here is iron. But here's the nice picture for it. My ugly picture? You don't want a nice picture? Alright. You drew this already? Yes. Got this? Okay. Ms. Sharif? Yep. Right. So, what I'm thinking, we'll do this one today, and maybe we'll do it by taking turns. 1, 2, 3. You do 1, I do 1. You do 2, I do 2. You do 3, I do 3. Or maybe we'll do them together. I don't know.
You do 1, you do 2 and 3.
It's an interesting idea, but I think we won't do that. Maybe we'll do them together then, bit by bit. But I'll give you a break for a couple of minutes. In case I forget later, remember I said we're moving the class earlier after lunch so you can finish sooner today. We'll use this room still because this room will be free. I know it said A41 on the timetable, but I'll still be in this room because I have a class after this class. So we'll use this room 12:50, because if we start at 12:50, we'll finish at 2:30.
You want to start at 12:50?
Yeah, because I'm going to still be in the room because I have the business students after you guys, so I can immediately start. And this way you can finish at 2:30. That should be good. This room, I believe it's free. Now, if something weird happens and you come here at 12:50 and I'm not here because there's another class, I'll be in the room that was scheduled on the timetable, which I think was A401.
Alright.
Yeah. All right. Just take 5 minutes, and then we'll come back and we'll do these together. Breakfast.
Yeah.
That's a terrible breakfast. A Kit Kat.
4:50 then.
Oh well, then.
Energy.
Yeah. You need to save your money for the car, yeah?
No.
No? You still have your car, don't you?
Yeah.
No, I'm full.
Sure.
I had 2 breakfasts. I had breakfast at home and in the canteen, so I am good. I don't think I'll have time for lunch today, so that's why I had double breakfast.
I don't like eating in the morning.
No! No. Some people don't.
Because back home I used to wake up late and was all messed up.